Okay, Assalamualaikum and good morning to all of you. It's me again, Dr. Siti Hafiza binti Muhammad Kazai, as you can see from the slide. Okay, the material of lecture prepared by Dr. Nur Syahidatul Akmal binti Muhammad Suhaimi, and it's me, Dr. Fiza, will be explain or discuss with all of you our last chapter, chapter 6. Okay, so for our last chapter, organometallic chemistry, CHM 676. Okay, uses of some organometallic compound. Okay, for our last lecture, for this course, okay, we are going to explore the uses of some organic metallic compound, okay, particular as a catalyst in the reaction. Okay. Okay. Previously in my last lecture, I was telling, or we will discuss with all of you about the reaction involved in organometallic compound, okay, such as organic compound that can undergo direction such as OA, reductive elimination. Okay, and for this chapter, okay, we will see how those reaction, okay, make it that compound can be as a good catalyst. Okay, from the previous lecture, okay, we already discussed the properties that involve, okay, with the reaction of oxidative addition, and also for the reductive elimination, which is reductive elimination will again or opposite the oxidative addition properties. Okay, so as just like catalytic properties of organometallic compound. Okay, as you can see, okay, this one is well known. Okay, there are so many reaction. Okay, there are so many reaction or compound that involve or that had been used to catalyze the reaction. Okay, so one of the most popular or famous reaction or catalyst compound that will be a catalyst, make it that the reaction more easier or more time consumer, low time consumer, just like our Grignard reagent. Okay, and so on. So the ability of organic metallic compound to undergo the combination of oxidative addition and reductive elimination reaction enables them to act as catalysts. Okay, there are many organometallic catalysts employed in the industry, and most of them works via the OA or RE, okay, oxidative addition or reductive elimination process that typically occur in cycle. Okay, so how, for the next slide, I will show you or we will discuss, okay, how the process that involve with those this kind of two reaction, okay, oxidative addition or reductive elimination. Okay, just to be prepared, make sure that you know how to calculate, okay, the ENS rule of the compound, and also you know how to determine the oxidation number of the compound to make it that the process of understanding can be more easier. Okay. Okay, so now first we start with the example number 1. Okay, the production of benzene. Okay, they use CP2 Okay, Cp2 tantalum, okay, trihydride as a catalyst, okay, through the deuteration reaction of benzene. Okay, the production of benzene. Okay, as you can see from the step 1 until step 5, okay, they are involved with reactive elimination and also the oxidative elimination. Okay, the uses of that reaction to produce the benzene. Okay, from the ordinary benzene, okay, as you know, our benzene have H. Okay, ordinary benzene use the Cp2 tantalum trihydride, okay, as a catalyst to produce deuteration. Okay, deuteron of hydrogen, okay, convert into D as a deuteron to the benzene. Okay, so they use one of our transition metal element or organic metallic compound as a catalyst. Okay, so here first of all I just refresh, okay, how to calculate, okay, the oxidation number of our catalyst. Okay, first of all, this is the initial step, okay, for the step 1. Okay, so our compound, okay, we have 2 Cp, okay, central metal, and also we have 3 hydrogen. Okay, so this one I show you how to calculate the oxidation number. Okay, so this one I state the Roman 5. Okay, so Cp have -1 charge. Okay, and for the hydrogen, and they have -1. Okay, total we have 5 oxidation number. Okay, so before we get through the first step, we also calculate the ENs. EANs, okay, total electron for our catalyst. Okay, so Cp have 5 electron, so 5, 5. So which is this one, 1, 1, 1. Okay, total up from the Ta for our central metal, tantalum group 5, so they have 5 number of electron. For 5 times 3 equal to 15, 15 plus 3, so total electron is 18 electron. Okay, so for the first step, the loss of H2, which is there are reactive elimination. Okay, so from the first reaction, as you can see for the second compound, from this one they have 5 ligand. So get through the first step, they lost hydrogen gas. So they have only 3 ligand. So when you calculate the oxidation number, we got 5. 5 from the 5 at the first. So after get through the first step, so they lost 2 ligands. So of course, so the oxidation number is 3. Okay, and for the total number of electron, also they reduce by 2. Okay, so 18 to 16. So the 5, 5 for Cp. So our central metal also 5. So 5 times 3 equal to 15. So plus 1 from hydrogen, so equal to 16. Okay, so they reduce by 2 for the number total electron, and also reduce by 2 for oxidation number. So that one is properties for reactive elimination. Okay, for the first step. Okay, for the second step, okay, so we have Cp2, our titanium hydride, okay, react with benzene molecule, which is oxidative addition can be occur to produce the third compound. Okay, so where the phenyl group is sigma bonded to the metal. Okay, so this one we have 3 ligand. So after do reaction with benzene, which is they use oxidative addition reaction, okay, through oxidative addition reaction. So the total number of electron make it that 18 electron. Okay, so that is oxidative addition to produce the third compound. Okay, so for the second step, and for the so now CP okay, so the aim for the reaction is to detrate, okay, detrate the benzene. Okay, we want to convert all the hydrogen at the ordinary benzene to the D. Okay, so the third step, our third compound, okay, undergoes a second loss of hydrogen gas, okay, which is through the reductive elimination to give another 16 electron species. Okay, so they lost another 2 hydrogen. Okay, for the third step, and for the fourth step they added of D2, which is this one is additive addition to form 18 electron species. Okay, this is for the step number 4. Okay, to produce the compound, so 1, 2, 3, 4, 5. Okay, compound number 5. Okay, so as you can see here, they involved with addition of plus 2 D2. Okay, and our last step, okay, they eliminate the benzene, okay, leaving behind our CP2 titanium deuterium. Okay, so we don't want the catalyst because of we already produce the D. Okay, H replace with the D. So step 2 to 5 are repeated to fully converted the 1 deuterium to all the H at the ordinary benzene with the D. Okay, so repetition of this sequence from step 2 to 5 in the presence of excess D2 eventually lead to the full deterioration of benzene to C6D6. In each sequence cycle, the catalytic species regenerated. Okay, so from the ordinary benzene, we use our catalyst, okay, to convert all the H with the compound or element D. Okay, so from the step 1 until step 5, they get through the reductive elimination and oxidative addition. Okay, so this is the easiest or the simplest reaction involved for the users, okay, of the organometallic catalyst. Okay, so before I move to the second example, so just keep remind that all of you hopefully can manage, okay, to calculate the total electron and know how to determine the oxidation number. Okay, now we move to the next example. Okay, so now we move to our second example. Okay, the catalytic process of Monsanto acetic acid. Okay, the production of acetic acid we call it as a Monsanto process. Okay, this reaction are being used in the industry, okay, to produce the acetic acid. Okay, okay, as you can see from the overall reaction, okay, the mixture of CO, okay, carbonic compound with hydrogen gas, which is we call it as a syngas, okay, through the catalyst of copper and zinc to produce the methanol. Okay, the first step is they want to produce the methanol, okay, from the syngas, the mixture of the syngas through the catalyst, so we produce the methanol. Okay, after they have produced the methanol, do their reaction with the catalyst of CO, okay, do reaction with the compound of CO, our rhodium, okay, and iodide at a certain condition to produce the acetic acid. Okay, this is the overall reaction to produce the acetic acid. Okay, so this one involved with our organometallic compound. Okay, so from the mechanism, okay, so the process of production of acetic acid involved with the 6 step. Okay, step 1 until step 6. Okay, from here also you can see they involve with oxidative addition in section of carbonyl and reductive elimination. Okay, in section carbonyl which is involved with 1,1 in section. Okay, so for in section we have to write previous class we already discussed 1,1 in section and 1,2 in section. Okay, for this one is in section of carbonyl, which is 1,1 in section. Okay, so the first step not involved with okay, our transition metal, but the first thing starting material is to produce the methanol. Okay, step 3 until step 5 are repeated in cyclic manner, while step 1 continue to supply the methyl iodide with a byproduct of water. Okay, so as you can see, we will discuss more into reaction. Okay, through the cyclic of reaction to be more easily to understand what the step 1 until step 6. Okay, so as you can see, these two reaction. Okay, step 1 continue to occur to supply methyl iodide to the system as shown below. Okay, as you can see, this one, okay, methanol is from the overall reaction. They are produced to react with our hydrotic acid. Okay, so this one, methanol actually produced from the mixture of syngas. Okay, so the first slide we already show that mixture of CO, carbon monoxide with do reaction with hydrogen gas, which is to produce, we call that as a syngas. Okay, with the catalyst of copper and zinc to produce the methanol. Okay, this one is the starting material, okay, that produced from the mixture of syngases. Okay, when we have the methanol, it will do the reaction with hydrotic acid, okay, to produce the iodide methane. Okay, so iodide methane and H2O. And for the step 6, complete the production of acetic acid by the reaction below. Okay, this one is a reaction. Okay, and the first, how the starting material can be produced, okay, to proceed to undergo step 2, step 3, step 4, step 5 until step 5 to produce our acetic acid. Okay, so from this acyl, okay, to get through the step 2 until step 5, as you can see from the iodomethane, okay, we already have C double bond O here, and do reaction with H2O to produce the acetic acid. Okay, and the last one, the last production is acetic acid. Okay, so these two reactions represented for the next cycle. Okay, so it more easier to see what the happen, okay, occur within that step 1 until step 6 from the cyclic manner for the process. Okay, okay, here is the mechanism for the production of acetic acid. Okay, last slide, it just show the two reaction. Okay, the first step and the last step. Okay, this one is more detailed about the production of acetic acid. Okay, as you can see, I have label for the step 1 until step 6. Okay, 1, 2, 3, 4, 5 and 6. Okay, so for the first step, starting material is our methanol. Okay, methanol that are produced from the syngas, mixture of syngas with the catalyst of copper and zinc. Okay, they have the methanol for the starting material. Okay, for the second step, the production of our compound, catalyst compound. Okay, rhodium with our cobalt, CO, carbon monoxide, and iodine. Okay, so total number of electron is 16. Okay, so how you get the 16 number of electron? So RH is group 9. Okay, oxide, carbon monoxide, they have 2 carbon monoxide. This meaning that we have 4 electrons. So this one also we have 4 electron. Okay, 2 electron times plus 2. Okay, so total up we get 17 electron. So as you can see, this one they have 1 minus, so that's why total kita minus, okay, reduct with 1, so we get 16 electron. Okay, so total electron. Okay, for the step number 3, okay, the third step. Okay, our catalyst do reaction with iodide methyl. Okay, iodide methyl come from our methanol do reaction with H2O and HI. Okay, methanol do reaction with HI to produce the iodide methyl. Okay, so they release the H2O. Okay, so between these two reactions, they have the oxidative addition. Okay, so as you can see from the second step to the step 3, okay, so 16 electron to the 18 electron, they increase by 2. Okay, so that is also properties for oxidative addition. So from the 4 number of ligand, so they increase into 6 number of ligand. Okay. Okay, so this one 18 electron, 16. This one is 18 electron. So we have 3 element of I. Okay, so they present of 6 total electron. So with this one we have 4. RH is 9 number of electron. So CH3 neutral. Okay, then total up we got 90. Okay, 90 electron. So we have minus 1. So 90 minus 1. So we got 18 electron. Okay. So for the next step is step number 4. Carbonate insection. Okay. Carbonate insection. Because we have methyl. So this one is 1-1. Right. 1-1 insection. Okay, 1 in section. And after that we get this compound, this molecule. So before and after we have the same number atau daughter electron. Okay, we have same daughter electron. So actually carbon in section is not the new CO attached to our metal. Actually CO is come from CO previously bonded to our metal. Okay, so they attach to the metal, so we got this new species. Okay, so and the step number 5. Okay, we want to produce the what we call it, our catalyst. Okay, so at this step involved with the reductive elimination. Okay, reductive elimination, which is they will eliminate acyl iodide. Okay, acyl iodide, which this product will do reaction with H2O, and the end of the step number 6, they will produce the acetic acid. Okay, so from here they eliminate the acyl iodide to produce this species, and another catalyst. Okay, another catalyst to keep that reaction occur again. Okay, continue occur to produce more acetic acid. Okay, so this one they reduce, they eliminate for the acyl iodide and do reaction with our HI. Okay, hydrochloric acid, do reaction with H2O, eliminate the HI to produce the acetic acid. Okay, so this one how you determine the reaction that will occur to the last one to produce the acetic acid. Okay, so